Okay guys, welcome back to Java Video Tutorials. This is lesson 14 and this lesson will be a quick introduction to recursion. Recursion is very important. It's not only going to be found in Java, but you will find it in just about every programming language you encounter. Some programming languages, for example Lisp, they don't even have things like loops, in which case recursion becomes your best friend. So first thing we have to do before we can get into recursion is understand a little bit what happens when we call a function. So I wrote out some code here. I created a class called recurse. Inside the main method I create a variable called x, give it the value 15, and then I create another variable called triple x, and I just want to assign it the value of this function call with triple one of x. Of course x is 15. After that it just prints out x, which is 15, and then x tripled, which we want to be 45. So that's beta version of Dr. Java. Don't know why that happened. Alright, so to triple x, let's go ahead and return x times, or n rather, times 3, because we pass in x to this function as n here, and we're going to return n times 3. So let's go ahead and compile that, run it, and of course we get x is 15, x tripled is 45. 15, 30, 45. So what exactly happened when I called triple one? Well, what goes on in memory is you have this this space of RAM on your machine called heap, and the heap is where we're going to store all the local information about where our program is when we call a function. So inside of our main method here, we have this local variable called x, and we have a local variable called triple x. But as soon as we get to this function called triple one, we need to temporarily put everything on hold and go over to this other function triple one, which is completely different space. And we don't know about this x, we don't know about triple x, we just have a job to do, and that is whatever's inside these curly braces. So we pass in this value x. That's how this variable from this scope gets over to the scope of this triple one function. So there's my Facebook updates. Okay, so if we threw me off. Okay, so what happens is this x gets saved in memory, and this triple x gets saved in memory, and another thing that gets saved in memory is which line of code is going to be executed next. So when triple one is called, we save all that stuff in memory, and we save it on what is called an activation record, and the activation record goes in a heap space. So you can imagine if, say, we call another function from inside triple one, we put triple one on hold, we give him an activation record, he goes on the heap space, and then we go do something else. So when we return out of this function after this return statement, what we do is we get the last activation record off of the heap or the stack, and then we know where we were. We know which line of code to execute next, and we have all our local variables back, and everybody's happy. So that's basically what happened. Now I'm going to show you another way to write triple. Let's say, for instance, that maybe somebody said you can't use the multiplication operator. So you're like, okay, well that's kind of a dumb requirement, but I can do it anyway. So let's say int result equals 0, and do a simple for loop. Int I equals 0, I is less than n, plus I, and result equals result plus 3, return result. Okay, if you look at this real quick, it's quite straightforward. And what happens is this loop just gets run the same number of times as this n value here. So if n is 15, this loop will run 15 times, and every time it will add 3 to this result variable. So we go 3, 6, 9, 12, 15, 18, 21, blah, 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 until we get all up to 45, which is the triple of 15. So when we return that, then that should be our happy result. So let's change this to 222 and go ahead and compile that. What did I do? Oops. Okay. Compile and run that again. Of course, we get the same result. So what's the difference between these two functions? This one has one line of code, and let me close down TweetDeck really fast. Okay, so this one has one line of code, and it uses the multiplication operator, and so when the program counter gets to this, it just goes bam, it executes that code, and it's like 1, maybe 2 instructions, or something like that. It's a constant number of instructions to do multiplication, no matter what n is, no matter what this value is. It's always going to be the same amount of time to your CPU. If you look at 222, we have a loop here. So the program counter, the line of code that executes, this line here will run more times depending on n. If n is a higher value, this will get run more and more times. So if n equals like 10 million, then this is the same thing as running like 10 million lines of code, which is a lot. It's not efficient. So this is not a good solution. Bad. This is a good solution. Fast, quick, easy. So the only reason I did this was to show you the difference. Now I'm going to show you a third way, and the third way is definitely not that intuitive. So let's go ahead and write it real quick. So this is going to be the recursive method, and what I'm going to do is triple 3 without using any, triple n without using any loops and without using the multiplication operator. So first step you need to write anything recursive is a base case. Base cases are usually so simple that you won't even be able to find them. You're always going to be trying to think too hard for your base case. So the way we come up with a base case is we say what value of n would make this the easiest problem in the world to do. Most people say 1, because 1 tripled is 3. And I'll tell you there's even an easier answer, and that is if n is 0. What is the triple of 0? It's just 0. So I'm going to start out with an if test. I'm going to say if n is equal to 0, then return 0, right? So far our program is correct. As long as n equals 0, then this triple function actually works. But now we need to do the recursive step, and this is where you need to have sort of like a leap of faith. And the way this works is we say otherwise, else, return 3 plus triple of n minus 1. So what this is going to do is, let's just do some, put some values in for thought here. So if I were to pass in n equals 1, first it's going to go through this if test. Is 1 equal to 0? No. So we're going to go to this else. Now it's going to return 3 plus triple of n minus 1. So triple of n minus 1 is equal to triple of 0, right? If n equals 1, 1 minus 1 is 0. So triple 3 of 0, let's go see what that is. So we come up here, we put a 0 in here. If n equals 0, return 0. So triple 3 of 0 is equal to 0. Return 3 plus 0. 3 plus 0 is equal to 3. The triple of 1 is 3. And if you want, you can you can just use that information and put in any number of n, and you can just go through and you can see how this is going to work. So let's go up here, change this to a 3, and compile that. And you'll see I've got x tripled is 45. Now here's a problem. This one is one line of code, one statement, one or a constant number of CPU instructions. This 222 is dependent on n for the number of CPU instructions you do. However, it's just one function. You're only calling 222 one time, and it doesn't call any more functions inside of this. So when you call 222, it puts one activation record on the stack. 333 though, he's kind of a different story. So we actually call another function which happens to be the same function from inside of 333. And what that means is it's going to keep adding activation records to the stack, to the heap. And so this also runs about the same number of instructions as this 222 function, but he adds those activation records on top. So he's using more memory and more CPU time. So that's probably the simplest possible case of recursion I can think of, is just doubling a number or tripling a number. You know, it's really easy, and it's pretty easy, I think, to understand how this works. Because if you have triple of 0, then you have triple of 1, because triple of 1 is just 3 plus triple of 0. So if you have triple of 1, which you just figured out, then you can do triple of 2. Triple of 2 is 3 plus triple of 1, which is 3, which is 6. So triple of 2 is 6. Triple of 3 is 3 plus 6, which is 9, right? So just keep going through, and eventually you've got all the numbers. Here's the problem. If I make x something big, like 5,000, how many activation records is this going to create? Well, about 5,000. Whereas these two, it's only going to use the same amount of memory. So let's compile that. See, it compiles fine. Now let's run it. So it actually ran. It did that pretty quickly. Got 15,000 is the answer. Let's make it 50,000, okay? Whereas 50,000 times 3 is essential for a computer. But there, you see I get these errors here. And it's a long string of errors. Go all the way up here. We get this stack overflow error. So I remember I was telling you about the heap space. That's also the stack. And when you try to call, when you try to make 50,000 activation records, that fills up real fast because your stack is tiny. So that's one drawback of recursion. But like I said, this is definitely not a use case that you'd want to use with recursion. You'd never want to triple a number like this. That would be silly. So I'm going to go ahead and show you another silly case. Let's comment all that out and put it down there. Everybody here probably knows about the factorial function. This is just another example of recursion. It's easy to understand, easy to write, and you see it a lot. So let's go ahead and write it. Alright, we're good. Let's see, public static int factorial int n. So you know how factorial works. Like if I say 5 factorial, that equals 5 times 4 times 3 times 2 times 1, which is, I think, 120, 20, 60, 100. Okay, yeah. So that's how factorial works. It's just the exclamation point means factorial, and then that's just the number times all of the numbers below it, integers below it, until you get to 1. And so as you can see, it grows really quickly, because 6 factorial is going to be 6 times 120. And then 7 factorial would be 7 times 6 factorial, and so it just grows super quickly. Let's go ahead and write this recursively. So the base case is, I'm not going to worry about 0 factorial, so let's just say the base case is with 1 factorial. What is 1 factorial? Well, it's 1. So if n equals 1, then I'm just going to return 1. Right? Easy enough. So right now our factorial function is correct as long as n equals 1. Else return n times, I'm just going to do this, factorial n minus 2 there. Yeah. N times factorial n minus 1. So if I give it a 2, it's going to say n times n minus 1, which is 1, factorial 1 is 1, so 2 times 1 is 2, 2 factorial is definitely 2. 3 factorial is going to be 3 times 2, which is 6, 4 factorial is going to be 4 times 6, which is 24, so on and so on and so on. My voice is getting tired. Alright, so let's create some tests here. Let's just go with 5 fact x equals and compile that. There we go. X is 5, x factorial is 120. Alright, so these are the most elementary examples of recursion. In the next video, I will go over more complicated recursion along with something called tail recursion, which is pretty cool actually. Especially with Java. It's not always cool, but it's cool with Java. So definitely come back, and if this made your head hurt, then you need to do, you might want to watch the next video, but you might want to practice some more. Like here's your homework assignment. Write a function that outputs the Fibonacci, not the Fibonacci, yes, the Fibonacci sequence. Series sequence. Let me think. How does this work? Fibonacci series. Yes, a series is when you add them up. Okay, so write a function that outputs the Fibonacci series for a given number. So it would be like public static int Fibonacci int n. And the way that works is the first two numbers are 0 and 1. So if n equals 0, then the Fibonacci of 0 is 0. If n equals 1, the Fibonacci of 1 is 1. And then for any number after that, you add the previous two numbers. So Fibonacci of 2 is a Fibonacci of 1 plus a Fibonacci of 0, which is 1. Fibonacci of 3 is these two values, so we'll put 2. Fibonacci of 4 is going to be Fibonacci of 3 plus Fibonacci of 2, so that's going to be 3, 5, 8, 13, 21, so on and so forth. So if I give you an n like 15, you better tell me what the Fibonacci of that n is. That's a pretty good assignment, and the only hint I'm going to give you is that you're going to have two base cases. So go ahead and try that. If you can't figure it out, send me an email and I'll help you with that. And this lesson's gone pretty long, but I think it was pretty good. So come back. I will see you later.